In this video, I'm going to go through the OCR AS-level Chemistry paper. This is the 2019 paper, and it's paper one. And I'll just do the first half of this paper in this video and the second half in a later one. Okay, so the first question is really just, you could do it with GCSE. Which statement about the periodic table is not correct? Elements arranged in groups with similar chemical properties, obviously true. Arranged in periods with repeating trends in the properties, yes, that's true. Increasing atomic number, that's true. The elements in the halogen group increase in reactivity down the group, that's not true. As you go down the halogens, fluorine, chlorine, bromine, iodine, they get less reactive because they like to form negative ions, of course. They like to attract an electron, so it's easier for them to attract an electron when they've got a smaller nuclear radius, okay, because the nucleus is closer. Okay, anyway, right. Question 2, a bit more difficult. Which molecule contains the largest bond angle? Now, let's have a look at ethene, the C2H4. You've got a double bond between the two carbons there. And the carbon has got 4 electrons in its outer shell, so it forms 4 bonds, and it has no lone pairs. So you have got, right, with no lone pairs around those carbons. We've got 3 groups around the carbon. The double bond you just treat as a single bond for the purposes of working out the shape. So that they're all going to, it's going to be trigonal planar. That's going to be 120 degrees. Now all of these other bond angles in these compounds are going to be smaller because, all right, they're all actually based on tetrahedral shape. I'm going to start off backwards with methane. So methane, you've got 4 bond pairs and no lone pairs. And the bond angle is 109.5. It's tetrahedral. Now, when you have nitrogen instead of carbon there, nitrogen has got a lone pair and he forms 3 bonds. So you've got a lone pair. That, of course, will squash that bond angle a little bit to 107.5, most people say. And if we go to replace that nitrogen with an oxygen, then you've got 2 lone pairs and 2 bond pairs. So the angle is even more squashed down to about 104.5. So yeah, A is the correct answer there. Right, what's the percentage composition by mass of nitrogen in ammonium carbonate? Okay, so the MR of ammonium carbonate is going to be, right, we've got 2 nitrogens, so 2 times 14. We've got 2 lots of 4 hydrogens, so that's plus that's going to be 8 plus 8. We've got a carbon, 12, and 3 times 16 for the oxygen. That gives us an MR of 96. Right, the percentage of nitrogen in that then is, we've got the nitrogens weigh that much, the 2 times 14, that's 28. So it's 28 over 96 times 100. And that gives us, I think, 29.17%. That is the answer, C. Right. This question is about atom economy, and have you worked out, it says, which is the most sustainable in terms of atom economy, i.e. we're looking for the highest atom economy. Right, now atom economy is the mass of the useful product over the mass of all the products. Let's call mass of useful and side products. Times by 100. Now, right. Rather than working them all out, let's see if we can see we want the highest atom economy. All right, let's see if we can see which one it's likely to be. Well, I think we can rule this one out because sodium bromide is very heavy. The byproduct is very heavy because bromine weighs 79, that's 80. And okay, so we can, 79 plus sorry, it's going to be 79 plus 23. So we can, the byproduct, the side product, yeah, is too heavy. So it's not going to be that one. D looks good because you've got a very light side product. You've only got water, 8, which weighs 18. So I think I'm going to highlight that one. This one also looks good because again, you're only producing water, which is quite a little small molecule, but this one will be lower. Right, this one's going to be lower because methanol, the useful product, weighs less than butene. So I think D is going to be the answer here. Let's just check the last one. Well, the last one, you're producing quite a lot of heavy stuff, right? So so it's not going to be B, no way. Okay, so D is the right answer, and that's sort of do it quite quickly without having to work out the atom economy for each reaction. Okay, so this is about volumes of gases. So we've got 2 moles of NO react with 1 mole of O2 to give us 2 moles of NO2 gas. Don't forget, if the same volume of gas, it has the same number of moles. It doesn't matter what the gas is. So let's see, we've got 80 centimeters cubed of NO. Now, that is going to need half the number of moles of oxygen. 2 moles of NO only needs 1 mole of oxygen. Make that clearer, sorry. So you have 80 centimeters cubed. It's only going to need half the volume of 80. You're only going to need 40 centimeters cubed. So that means at the end, because we've got, sorry, it's 8 dm cubed, sorry. 8 dm cubed is only going to need 6 dm, 4 dm cubed of oxygen. So that means we are going to, because we've got 6 dm cubed up there, we're going to have 2 left over. 2 dm cubed left over. All that's going to react. But 2 moles of NO gives us 2 moles of NO2, so that's going to make 8 dm cubed. Right, so the total volume of the product is going to be 8 of the NO2 and 2 of the oxygen, which is left over, so that's going to be 10. So the answer is B. Okay, now we have to use the ideal gas equation for this one. It's not standard temperature and pressure. What's the volume of 0.01 mole of nitrogen? Okay, so we need to convert this into Kelvin. So add 273. So that is going to give us 623 Kelvin. Don't forget this needs to be converted to pascals before we put it into the ideal gas equation. And we've got, we have PV is equal to nRT. Volume is going to be equal to nRT over P. You've got to be really careful with the units here. So number of moles, 0.01 multiplied by R, 8.31, that's the gas constant, multiplied by the absolute temperature, 623, divided by the pressure in pascals, not kilopascals, and that's going to give us our volume in meters cubed. Okay, so we do that. That gives us, we'll just work it out. That gives us 2.58 times 10 to the minus 4, 2.59 times 10 to the minus 4 meters cubed. Okay, now how many centimeters cubed are there in a meter cubed? There are, maybe surprisingly, a lot. There are 1 million. So 10 to the 6 centimeters cubed is equal to 1 meter cubed. So to convert this into centimeters cubed, we times by 1 million. Okay. And that gives us 259 centimeters cubed. Centimeters cubed. So look, they're trying to distract us with that. It's not the right answer. This is the one there. Okay. So that's just about knowing your units, as is always the case with the ideal gas equation. Right, now, 0.24 grams of an element is reacted with 0.01 mole of chlorine to form a chloride with that formula. Okay, so that means if we've got this many moles of chlorine, we need 0.01 moles divided by 2 moles of X, because it's XCl2. That's obviously equal to 0.005 moles of X. Now we know that moles is equal to mass over AR for an element, relative atomic mass. We want to find out AR of this element, so rearrange. AR is equal to mass over moles. Our mass is 0.24 grams, they tell us there. The number of moles is 0.005. Okay, so that is going to give us an AR of 48. And you look in your periodic table, which of those elements has a relative atomic mass of 48? It's titanium. D is the answer for that one. Okay, a phosphate 5 ion has that formula, PO43 minus. What's the formula for copper 1 phosphate? Right, in copper 1, we have the 1 plus ion. So that means we're going to need 3 coppers, yeah, for every 1 phosphate ion. So the formula is Cu3PO4. And there we have that one there, D. Okay, which reaction shows chlorine only being oxidized? Okay, so I think there's quite a lot of disproportionation reactions in these. That's where chlorine's oxidation number goes up and down. Right, so let's do A. Obviously 0 is the oxidation number in chlorine. The oxidation number in HCl is going to be of chlorine is -1, and in the hypochlorite it's going to be +1. So chlorine's been oxidized and reduced, so it's not that disproportionation. Here, oxidation number of chlorine is in ClO2 is going to be +4. I think this is another disproportionation. In that compound, it goes down to +3, and that one goes up to +5, so it's not that one. This is definitely a disproportionation, so we've got +5 oxidation state for chlorine there, and there it's +7, its maximum oxidation state, and there it's -1, so that's disproportionation. It's got to be D. Let's just check it. So yeah, we've got chlorine with an oxidation number of -1 there. It's -1 in that, in MnCl2, but in here, obviously, it's 0. So 2 of the chlorines have been oxidized. None of them have been reduced, so D is the correct answer. Right, so reaction profile here we've got here. Now, first of all, the activation energy of the forward reaction is 120. That's wrong. The activation energy of the forward reaction is 150, isn't it? It's that hump there. So that's wrong. The activation energy of the reverse reaction is 270. Well, the activation of the reverse, you've got to go from down here to up there. So that's 120 plus 150. That is 270, so that is correct. Let's just check the other ones. The enthalpy change of the forward reaction is -30. That's wrong. The enthalpy change is from there, that height, down to there, which is -120. That's wrong. The reverse reaction is exothermic. No, it's not, because look, the reverse reaction, the products have got a lower chemical energy than the reactants. So some chemical energy, the chemical energy has gone up. That means thermal energy has been converted into chemical energy in the reverse reaction. That is an endothermic reaction. So B is our answer. Hydrogen and chlorine react as shown below. Which statements? We've got hydrogen H2 react with Cl2 to form HCl. Which statement about this reaction is correct? Right. It is exothermic. It was minus. Less energy is released on bond making than is taken in. That's wrong. That would be the case if it was endothermic, and it's not. It's exothermic. The enthalpy change for the reverse reaction is that's correct, because it's just going to be the same number as the forward. Change the sign. The enthalpy change of formation of HCl is that? Well, it's not, because it looks like we're forming HCl, but we're actually forming 2 moles of HCl there. So delta HF of HCl is going to be half of that value, 72.3. So that's wrong. Okay, we're forming 2 moles of HCl. That's why. The temperature decreases during the reaction. It's exothermic, so it won't. It will go up. So B is the right answer there. Okay. Right. The main reason for increase in reaction rate with increasing temperature. Right. A, the activation energy doesn't decrease with temperature; it stays the same. The catalyst will reduce that, of course. The activation doesn't change. B is wrong. More molecules have energy greater than the activation energy. That is going to be the thing that's really driving it, making it go much faster. The molecules collide more frequently. That will make it go a bit faster, but not as much as this one here, C. So C is the right answer there. Right. A catalyst is added to a system at equilibrium. What is the effect on the rates of the forward and the reverse reactions? Well, of course, it will speed up both by the same amount. Okay, so let's see, that one is wrong. B is correct. The rate of the forward reaction doesn't increase from one, then these two are obviously the opposites, but they're both wrong. Okay, B is the answer there. Right, what's the best description for the bonding between carbon atoms in an ethene molecule? Well, it's a double bond, isn't it? We have one of the electron density between them, that's the sigma, and then you have the second bond where the electron density is above and below the plane of the molecule. There's two sort of nodes to that, and that's the pi bond. Okay, so one pi and one sigma bond is one sigma, that's a sigma sign, and one pi bond. That is the correct answer. Which compound is unsaturated, alicyclic, and contains an alkyl group? Well, this is cyclic, but it's not alicyclic. It's an aryl group. You've got electron delocalization there, so it's not that one. This one is not unsaturated, so forget that. This one is the cyclic bit is unsaturated. It's got a double bond in there, and it has got an alkyl group. It's got this methyl group stuck onto it. That's the right one. Okay, D is not unsaturated. It's the ring. There's no unsaturation in the ring. It's saturated the ring, so it's not D. No double bonds in the ring there. Right, which statement about an electrophile is correct? Well, let's think about a stereotypical electrophile. We're going to have ethene, say, reacting with hydrogen bromide. And we have a partial positive charge on there. The first step in the mechanism, that pair of electrons goes on to the hydrogen. Okay, so is the hydrogen accepting a pair of electrons? It is. That's correct. Is the electrophile a proton donor? No, that is the definition of an acid is a proton donor. That's not right. In that case, that is actually, I suppose it is donating a proton, but if you had this as the electrophile, bromine, then it's still an electrophile, delta positive, but it's accepting a pair of electrons. It's not giving away a proton, so that's wrong. It's not a negative ion. In fact, it wouldn't. If it was a negative ion, it wouldn't be a good electrophile because it wouldn't be attracted to negatively charged things. And then a species with an unpaired electron, of course, is a free radical, which is uncharged, but it's nothing to do with this. That's a free radical. So A is the correct answer. Right, a section of a polymer is shown below. Right, it's going to be an addition polymer, so that means we've got to have a double bond. So it's got to be either C or D. Okay, so let's see what would happen if you had C polymerizing. So I've got two carbons with a double bond, and I've got on this carbon I've got two hydrogens. On this one I've got a hydrogen and a nitrile or cyanide group. Okay, well, how is that going to polymerize? I'll draw another one next to it. What happens, of course, is that we break the double bond and we form a new bond there. Okay, so you can see that this is carbon number 1, 2, 3, 4. Let's draw it in that diagram there. That's carbon 1, that's 2 with the cyanide come off it, 3 with the CH2. Yeah, this is carbon number 3. 4, and that's got the cyanide and gone. So that is the right answer. Let's just check D is the wrong answer. Let's see why. I'll do it in green here. So we're going to have the, that's not green, that's red, but let's do that. We've got Okay, so we've got an H and a cyanide on both carbons. Okay, so when that formed a polymer, it's not going to look like the one we've got up there, because you're not going to get this CH2 carbon every other one, are you? You're not going to get that CH2. Every single carbon is going to have a cyanide and one hydrogen. That's not what we get. So C is the answer there. And I would always draw those out. Rather than try and doing it in your head, it may think you're saving time, but you're much more likely to get the correct answer if you draw it out. Okay, which compound is not likely to have a fragment of MZ43 in its mass spectrum? Right, now 43 is when you have 3 carbons, okay, and 7 hydrogens, C3H7, and that's the fragment, okay, and it's sort of fragmented there. Right, in this one, D, we can get that fragment, no problem at all there. Yeah. In C, we can get a fragment which weighs that as well. Look, if I just have a look at this one here, that weighs 43 if you add it all up. Right, now the other two, right, let's see, this weighs 15. That's 15 for that bit, for the methyl group. Then we've got a carbon which is 12, so that's 27. Plus this oxygen which is 16, that weighs 43, okay? So that does weigh 43. So the answer must be A. Let's just see what we could get out of A. Well, we could get that, which is 29. That's a likely fragment. Let's think if we had this one, this here, that weighs 45, not 43, so that's not going to work. Okay, and various other combinations doesn't work. So our answer is A. Right, which statement about infrared radiation is not correct? Okay, infrared radiation causes some covalent bonds to vibrate more. That is true. Some covalent bonds, most covalent bonds, unless they are, will absorb infrared radiation, and that increases the vibration. Absorption of infrared radiation by some gases is linked to global warming. That's correct. It's by carbon dioxide chiefly, isn't it? By methane also. Infrared radiation is used to monitor gases causing air pollution. That's true. It's you can continuously monitor it. You don't have to do any chemical reactions or anything. So that's a good way of doing it. This one there is wrong. Okay, the action of infrared radiation on CFCs leads to the formation of chlorine radicals. Okay, right. I'm trying to confuse you here, because yeah, if you get compounds containing a carbon chlorine bond, yes, they can be broken and it causes chlorine free radicals, which causes depletion of the ozone. But of course, it's not UV that does that. It's not infrared. It is UV radiation that does that. UV is higher in energy than infrared. Infrared is not strong enough to break those bonds. It just may cause an increase in vibration, but it won't break them. Okay, and you should know the conditions for free radical substitution, of course, is UV light. Okay. Right, number 20, an unknown compound produces the infrared spectrum, and they give us some alternatives there. Okay, so we can see we've got carbonyl groups, we've got alcohol groups, we've got carbon-carbon double bonds in some of those. Okay, now let's have a look what we've got. This one here, this deep semi-broad peak at about 1700 is very, very characteristic of a carbonyl. Okay, you have to be a little bit careful because it is quite close to the alkene value, but it's just a little bit too high. That's on 1700, and look, that's a bit less than 1700. Another thing, that alkene, when you see it, is always much sharper and not as deep. Okay, that also gives it away. That is definitely a carbonyl from its shape and from its position in the spectrum. It's definitely a carbonyl. This thing on the left here is most definitely an alcohol OH. Okay, right. I shouldn't really circle the whole thing. It's that. Let's see. The bit in red. This is the alcohol OH. Yeah, and it's very easy to spot. It's quite broad, and it is next to this bit here, which is the CH, which almost all compounds have CH in it. So that's a dead giveaway for an alcohol. So we're looking for an alcohol and a carbonyl. Now, just that is not, it cannot be a carboxylic acid OH. If you look at the carboxylic acid OH, where's it gone? Right, there's our alcohol OH, okay? That's at 3,200 to 3,600. The carboxylic acid is much broader for a start, much broader, and is pushed to the right of the spectrum. And the carboxylic acid, right, it gets so pushed to the right of the spectrum, it swallows up that CH, and that's quite an easy way to see it. So if you ever see a peak like this, that sort of thing, very broad, like that yellow one, that's a carboxylic acid, and we haven't got one of those where it's swallowed up the CH peak. So we've definitely got this and this. So let's look at the molecules we've got. Right, it can't be A because A is a carboxylic acid. We said we hadn't got the. It could be B because we've got a carbonyl and we've got the alcohol group. That's good. So B is most likely. C, it's not going to be C because there's no trace for an alkene. There's no absorption for an alkene. Yes, we've got a DOH. And it can't be D because there's no alcohol present in D, and there's definitely an alcohol in that trace. And also we haven't got the carbon-carbon double bond there. Okay. Atomic structure 21. A question about atomic structure and the compounds of calcium, nitrogen, and oxygen. Most elements contain different isotopes. Two differences between isotopes are the same element. Right. The most obvious one, the easy one, is different number of neutrons. Now, I would say the safest thing, the next one to say the difference, I'd say different atomic mass, which seems like cheating a little bit because it's got a different number of neutrons. Of course, it's going to have a different atomic mass, but that is allowed. Don't say differences in chemical reactivity because there are not any differences, right? You can get away with saying slight differences in physical properties, but I think that's a bit dangerous saying that. Best just to stick with those two. Okay, this is a bit GCSE, this question. Complete the table for an atom and an ion of two different elements. Right, this first one has got 0 charge. Right, so it's got the same number of electrons as protons, so it must have 26 electrons. Its mass number is 26 plus 28, which is equal to 54. Now, which element is? We can't tell by looking at the mass number. We need to look at the protons, the atomic number. Well, that has got to be, look in your periodic table, the only element with 26 protons, atomic number 26 is iron. Right, this next one then has got a 2- charge. And it's got 36 electrons, so it's got 2 more electrons than protons, so it must have 34 protons. How many neutrons has it got? Well, we do 80 minus 34, which is equal to 46 neutrons. And which element is that? Well, we've got to look at the number of protons. Atomic number 34. It is selenium. Okay, one that you probably wouldn't know off the top of your head. I didn't. But it makes sense because selenium is actually in group 6, so it would tend to form 2- ions. It's below sulfur in group 6. Okay. Electronic structure then. Electrons occupy orbitals, which are arranged in energy levels. In the diagram below, okay, blah, 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 label the subshells and put in the arrows for the element oxygen. Well, oxygen is atomic number 8, so it's going to be 1s2, 2s2, 2p4. So that's 1s, that's got to be 2s, and there's 2 electrons in there, 1 up spin, 1 down spin. Then we've got 4 electrons in 2p, and we have to be careful here because, of course, they don't occupy, they won't pair up until they've got 2, so you're going to have 3 like that, and then 1, only they only pair up in one of the p orbitals. Okay, that's that. Okay. Calcium reacts with nitrogen to form calcium nitride, which is an ionic compound. Okay, so we need to look at the electronic structures. Well, we don't need to look at the full electronic structures, but we do need to realize calcium is in group 2. So it's going to form calcium 2 plus ions. Nitrogen is in group 5. Its electronic structure is 2,5. Now, it doesn't often form ionic compounds because the N3, it will form the N3 minus ion. It will gain 3 electrons. That is not very stable. There's too many electrons, too much concentration of negative charge on such a small ion. So the nitride ion doesn't form very often, but we can see what would be the formula of if we have a calcium 2 plus ion and N3 minus ion. We have to have 3 of those and 2 of those. So it is calcium 3, Ca3N2. Okay, which they tell us, sorry. And let's draw the dot cross diagram then. Right, so calcium, we just draw the outer shell. I think, right. Right, so I'll draw the outer shell, which is for the calcium is going to be 2, 8, 8, 2. So the calcium ion, we lose those 2. So it's got 8 in the outer shell. Okay, and the charge on that ion is 2 plus. It's lost 2 electrons. The nitride ion has gained 3 electrons. So that is going to be, it's got 5 of its own electrons, and then it's got that one, and that one, which have come from calcium. So that is going to be 3 minus, and we're going to have to multiply that one by, don't you need to do this for the answer, 3 of those for every 2 of those. Okay, done that. Now, the next question, they've asked this a lot. Calcium, well, they've asked how a nitride ion reacts with water. How does it react with water? And it tells you it forms 2 alkaline compounds. And I've had people saying to me, well, how do you know what those alkaline compounds are? Well, right, let's think what we've got there. We have got the N3 minus ion, okay? It is very highly negatively charged. That means it's going to be very good at pulling protons, H pluses, off water molecules. Well, if you add 3 protons to that, what do you get? NH3 gas. That is an alkaline compound, isn't it? Yeah, so that's what we get, the nitrogen. Calcium is going to react, well, calcium, and well, let's think, if you remove, you know, the nitrogen here, this is removed protons from water. What you get if you remove protons from water? You get OH minus ions left over, and they are alkaline. Now they've asked this, how does a nitride ion react with water on several occasions? So I would definitely learn this. It's only 2 marks, but it does seem to come up quite a bit. So you want to have calcium nitride, which is Ca3N2 plus water, is going to form, right, it's going to form calcium hydroxide, which has got that formula, because calcium is a 2 plus ion, and you're going to form ammonia, which is NH3. You're going to form 2 ammonias. We're going to have to form 3 of those. So that means we need a total of 6 oxygens. So we need 6 water molecules. Just check we've got the right number of hydrogens. Well, we've got 12 on the left-hand side here. Well, we've got 6 in the calcium hydroxide, and we've got 6 in the ammonia. So we've got 12 on the right as well. Okay. All right. Calcium reacts with oxygen to form a compound which is a giant ionic lattice. The diagram shows the ions. Complete the diagram by showing the symbols of the ions, including the charges. Well, obviously, calcium, we've said, is in group 2. It's going to form Ca2 plus ions. Oxygen is 2, 6. That always forms an oxide ion when it forms ionic compounds. Okay, so I'm going to put in a calcium ion there, and it's going to be, its next door neighbors are all going to be the negative one. So that's going to be an oxide. That's going to be an oxide. And also this one here. Sorry, the 2 should go on the top. Okay, and you're going to get next to that, right, that's going to be surrounded by calcium 2 plus. That will be a calcium 2 plus. That one's got to be a calcium 2 plus. And this one here connected to the calcium has got to be an oxide ion. So alternate positive and negative ions. Right, now this is a tricky question. Nitrogen forms an oxide with the formula N2O, okay? And a molecule of N2O is linear and has nitrogen at the center of the atom. Now, what's going on here? First of all, let's think about nitrogen likes to form how many bonds, and how many bonds does oxygen normally form? Well, nitrogen always forms 3. So if it's joined, there's a nitrogen in the middle, so if it's joined to another nitrogen, really, you can't have that. It's got to be a triple bond, hasn't it? Which doesn't really leave much. What's going to happen with the oxygen? But don't forget, nitrogen has got a lone pair. It's going to have a lone. Well, they both can have a lone pair on them, and that can form a dative bond to the oxygen. Okay, and that would give oxygen a full outer shell. This would be linear because we haven't got. There would be no lone pairs in this molecule. That lone pair I've drawn there is forming a dative bond. It's not a lone pair anymore. It's a bonding pair. And of course, the triple bond is just counts it as 1, so that would be a 180 bond angle there. Let's just draw that then. So I'm going to have N. Nitrogen is in group 5 of the periodic table. We're forming a triple bond, dot cross, dot cross, dot cross. Okay, that's one nitrogen. That's the other one. Right, the nitrogen on the left, I've drawn 3 of its 5 electrons, so it has a lone pair there. The nitrogen on the right, it has, I need to draw a lone pair there, and that is the one that's going to form a dative bond to this oxygen. Oxygen is in group 6, it's got 6 of its own electrons, so they're going to be like that. So the oxygen has a full 8 electrons in its outer shell. That is the, it's nitrous oxide. That is the correct diagram. Okay, now I think that takes us about halfway in the paper, so I'm going to leave it there and do the next one in the second half in the next video.